survey type lecture, I would like to present results that are known so far. I will present results from 3 papers. In the first paper, I introduced this concept so that it coincides with total domination in generalized prisms. I will explain a little bit later what is the purpose of this. Then in the second paper that was co-authored by Kari Aujakian and Ristas Krakowski, we derived some bounds for this new invariant in terms of total domination, ordinary domination, and carry mode domination. And in the recent paper with Tadea Kraner-Shumeniak, we explored complexity of the rainbow total domination. So we also explored this new invariant in context of rooted products because we found along the way that this could be useful. Yeah, I will also mention some other results that were known already before along the way. Well, since the name of this workshop is domination theory and its application, I believe we are all familiar with these definitions, but just in case, let us recall them. A dominating set is a set of vertices in a graph such that every vertex is either in the set or is adjacent to a vertex in the set, and the domination number is the minimum size of a dominating set in the graph. So with these red vertices, I denoted here one dominating set, but it is not optimal. We can dominate this graph with 2 vertices, as you can see here, but we cannot do it with 1, obviously. And the total dominating set is a set of vertices in a graph such that every vertex, including these vertices in the set, they must have a neighbor in this total dominating set. And the minimum size of a total dominating set is a total domination number. And of this graph, this is 3. Okay, as regards application, we often consider it as a model for solving problems in different areas, such as resource allocation, network coverage, social influences, and so on. And if we take a look at this resource allocation, we know that vertices in a dominating set, they provide a service or a product in such a way that all other vertices in the graph have access to this type of resource. And now you can imagine a more complex version of domination where we have k different types of resources or products or services. And we want to distribute them over the network in such a way that for each vertex that does not have any resource on its own, it sees all types of resources in the neighborhood. So for instance, in this example, in this sketch, we set k to be 3, and I see that this vertex that does not have any product, service, or whatever it is, it sees all 3 so-called colors in the neighborhood. Yeah. Also this one, it sees 3 here, and it sees 1 and 2 in the same vertex. We can put many products or services in the same vertex. And from now on, because of simpler notation, I will just write these numbers of elements. I will not write the whole set. Yeah. So if we take a look at the formal definition, Breschar, Henning, and Roll, they introduced this concept in 2008. And they say that a k-rainbow dominating function is a function that assigns the vertices of the graph subsets of this set of so-called color. You see here, they are numbered with numbers from 1 to k, in such a way that the union of a vertex to which empty set is assigned is the union of labels in the neighborhood. I mean, is the whole set. Yeah. This is what we saw here in this sketch. And the weight of a dominating function is just the sum of cardinalities of all let's call them also labels. These are labels of these vertices. And also I will say if some vertex is labeled with empty set, I will just call it empty set sometimes. Okay, and then they defined the K-rainbow domination number as the minimum value of the weight over all K-rainbow dominating functions of G. So just to be sure that we are not too quick with the definition, let us take a look at these two examples with two rainbow domination equal to 3. You can see that vertices I didn't put any label on. This means they are empty. They see both colors in the neighborhood. Yeah. And you can also easily see that we cannot do it with only 2. This number cannot be 2. Also for this graph. Okay. For those who are interested in this concept, I would like to invite you to take a look at this survey on K-rainbow domination by Boštjan Brešar, and in it he mentions that while it is not clear how often situations where K-rainbow domination could be applicable in practice, they had a strong motivation for introducing this concept. Namely, it is inherently connected to Cartesian products, and it has potential consequences for the famous Weising's conjecture you can see here above. Yeah, the Weising's conjecture says that the denomination number of the Cartesian product should be at least as large as the product of domination numbers of the factors. Yeah, so what is Cartesian product? Let us recall, just in case, what is this? Well, you can see formal definition here in this block, but it is useful to consider it as graph which can be constructed in the following way. So I will draw the Cartesian product of a path on 3 vertices and the complete graph. And for vertices, such graphs are called generalized prisms. And then we make a copy of each graph for each vertex that we see in the G graph. Yeah. So for this vertex, I make a copy, and then because I have another 2 vertices in G, I end up with 3 copies of K4. Yeah. And then we put another and then we put edges according to edges that we see in G. So we just connect vertices in these copies which correspond to each other. This vertex and this vertex, and also this vertex and this vertex correspond to each other. So I have 2 edges like this, but no edges from here to here because I don't see it in the original graph G. And we do this for all vertices that correspond to each other in H layers. So we have P3 times K4 here. And now that we understand the structure of the Cartesian product, we can take a look at this bijective correspondence between the set of all K-rainbow dominating functions of G and the set of all dominating sets in a generalized prisms. So let me explain this picture. I have graph G here and complete graph here. Vertices of K are denoted by numbers from 1 to K. And as we saw before, if I have such an edge here, this green one, then I have it also in the Cartesian product, and vice versa. It also holds. Yeah, so we have this structure. And now I would like to explain briefly why this equivalence holds. Yeah, so let's start with a dominating set in the generalized prism. I denoted vertices from it with I picked this blue color. These are the KK layer. This is just graph which is isomorphic to KK. Yeah. And if I see a vertex from D in here, sorry, can you hear me? Because I see that my internet connection is not good.
Yes,
can
we can. Yes, yes.
Okay, thank you. There was some notes, so I was afraid you cannot hear me. Thank you. So if we have this blue vertex here from a dominating set, then I just take a look, how was it denoted originally in KK graph? And I just put K down below in this labeling of this vertex that corresponds to this KK layer, okay? Also, because this one is the dominating set, I will put 3 here. And similarly, I have 4 here, 2 here, so I will label this vertex in G in such a way. And now I claim that with this, I get K-rainbow dominating function. And this is really easy to see because I only have to check vertices to which empty sets are assigned. Yeah. And I have to check that they see all the labels, all the colors in the neighborhood. But since this is empty, why is it empty in the first place? Because there is no vertex from D in this layer. That's why it's empty. But this means that these vertices need to be dominated within G layers, right? So this vertex is dominated by this vertex, and this automatically means that one will be in the neighborhood of this vertex labeled with empty set, and this must hold for every vertex in this KK layer. So you can see now that this really is a K-rainbow dominating function, yeah? And vice versa is also clear. We start with K-rainbow dominating function in G, and then according to these labels, I pick these vertices, I label them with blue, and then I say these blue vertices will form my set D, and then it is also clear that this will be dominating. Of course, if I have some blue vertices in these blue layers, then they're certainly all these vertices dominated because this is just the complete graph. And for those that are empty, well, I know that this neighbor, this vertex has to have a neighbor in this layer. So it is dominated, right? So with this, we actually proved this theorem by Breschar, Henning, and Roll, that these two numbers coincide. Yeah. Okay, we proved this inequality right now. One of the author was Doug Roll, who in 2018 came up with the idea, why not introduce independent K-rainbow independent domination in graph in such a way that it would be easier to explore independent domination in generalized prisms. Yeah. And then I thought, why not introduce some new domination invariant such that it would help us to explore total domination of these generalized prisms, because these two concepts turned out to be useful, because instead of looking at the whole big structure of Cartesian product, you can only take a look at the base graph, the problem in this way. Yeah, so I introduced this K-rainbow total domination number so that it coincides with total domination in generalized prisms. Yeah, and in order for these two concepts to coincide, the definition should be the following. To the condition we saw before that each empty vertex needs to see all the colors in the neighborhood, we must add a condition that if a vertex is colored with only one color, then this color needs to appear in the neighborhood of this vertex. Yeah. So we just have to check empty sets and the ones who are labeled just with one color. The weight is defined the same as before, and the K rainbow total domination number is just the minimum weight of a K rainbow total dominating function. We go over all such functions. Yeah. Let's take a look at this example we saw before. We saw that the rainbow domination number of this graph is 3, but 3 is not enough to totally rainbow dominate this graph. Why? Because this one does not see 1 in the neighborhood. Yeah, that's the problem, which we can solve either in this way to put 1 here so that this one also sees 1, or we can just relabel the vertices in such a way. But if you play around with this graph, you will see that you cannot do it with less than 4. Okay, I would also like to tell you that I had a problem of for naming this invariant, because the name total K rainbow domination was already taken twice, in fact, for 2 different definitions. Yeah, and I really wanted the name to be something similar, K rainbow, because of obvious reason, and I needed this word total. So why? Because I really wanted this name to be similar to the original one, because it really has to do something with Cartesian products. Namely, these 2 definitions, they have nothing to do with Cartesian products. They are different, and they are different from our concept. How they differ, I don't have time to explain now, but you can see some explanation in the first paper I mentioned. So then nothing else came up to my mind except for switching these 2 words. I know this is not the best solution, but nothing else came up to my mind. So what I want to say is just be careful when Googling for the papers on this topic, that these definitions are different. Okay, now I will go briefly through the results of the first paper. We will start with some really easy observations. You will see that if a graph does not have isolated vertices, then this concept coincides with total domination. I will leave you as a homework to derive this equality the same way as I did before for ordinary domination. And another observation is trivial. If we have K larger than the order of the graph or equal, well, then you can label each vertex just by 1 and you get proper labeling. And obviously you cannot do it with less. So this KRT number in this case is just the cardinality of the graph. So these cases are not interesting for us. And if n is greater than k, then this bound is obvious, right? And the first result that was proved was the characterization of graphs which attain this bound. And you can see that these are the graphs that contain spanning subgraphs that are isomorphic to complete bipartite graphs, where the first partite set, I mean, it doesn't matter which one, but I usually think of the first one as the one which has less vertices. So this cardinality of this first partite set is at most half of k, yeah? And you can see how you can label these vertices. You just have to make sure that you put 2 labels into each one and that all colors are used. And that's basically one thing behind one implication, and the other is also fairly easy to see. So I will go to a more interesting theorem, which states that if I have a graph without isolated vertices, and if k is at least 2 times the maximum degree of the graph, then gamma KRT will be n2. I proved this with some weight redistribution technique, or This is more known as discharging method. Unfortunately, I don't have time to explain every proof, but I will show you how this technique works in some example later. Yeah, so if we want to explore now the paths and cycles, for instance, then we see that due to this theorem, the only interesting cases are for K2 and K3. Yeah, but for the case K2, something was already known before this concept was formally introduced, namely Azaria, Henning, and Claujar. They explored total domination of hypercubes. Yeah, and along the way they proved this theorem. You will see many times today that if G is a bipartite graph, then the total domination number of prism over ordinary prism over G is 2 times gamma, or in our language, 2 rainbow total domination number of G is 2 times gamma if G is bipartite. And I also considered cycles of length 6 times something plus 1, and they obtained this. Yeah. So from this result, it is easy to derive formula for paths and even cycles, because gamma is known for those. Yeah. So that was already known, and also by the result of Henning and Yale, this one, they proved this bound on total domination. You get this. So the case K is equal to 2 was not that hard. I mean, not hard at all, because we could use all those known results to derive this complete formula. But more interesting was the case for 3 rainbow total domination of cycles. And you can see here also formula for paths, but let me just show you what is behind the proof for the cycles. Okay, for n equal to 3 and 4, the proof is direct, and if n is at least 5, then let f be a 3 rainbow total dominating function of Cn, and let us call this cardinality of this label the weight of f. Yeah. And now we'll define a new function which will redistribute initial weights under f. Yeah. So we do the following. If a vertex has initial weight 3, then this vertex gives a part of its weight to vertices in the neighborhood which are empty, and they contribute to them exactly 4/5. Yeah. And if initial weights are 1 and 2, then vertices contribute 1/5, respectively 3/5 to each neighbor, which was initially empty. And in this way, because we just redistributed the weights, we keep the total weight. Yeah. And because of the structure of the cycle, every vertex has only 2 neighbors. And if you play according to these rules, then you can see that the new weight is at least 4/5 for every vertex in the cycle. So this means this inequality is proved. Yeah. And for the opposite inequality, it is of course easier, because you just find construction. For small graphs, you can see it here, but for larger cycles, then patterns just they just repeat. Yeah. Now moving on to the results of the second paper. First, we proved the closed formula for complete bipartite graphs, which was, to our surprise, not that simple as we thought initially. And the motivation for finding this number was, in fact, in proving tightness of the results that follow. For instance, if we compare k-rainbow total dominating functions whose parameter k differ, yeah, we obtained this bound, and here these complete graphs served as an example for proving the tightness of this bound. Okay. From this proposition you saw before, from this proposition, take a look at this, and now you'll see that if these parameters differ only by one, then this bound can be derived. Yeah, and the lower bound is also fairly easy to see. So we have here a full description of how the rainbow domination numbers compare when the parameter is increased by one. And as I said before, tightness for the upper bound is proved by these complete graphs, and the lower bound is attained for graphs that look like this, as you can see below here. Maybe this result is not so interesting on its own, but it was a step towards more interesting comparison, which is comparison with total domination. And by theorem that we just saw, we obtained this sequence of inequalities. So we have this bound, yeah, this inequality, and the upper bound is obvious, yeah, because you can imagine a total dominating set in the graph, and then you just put all the colors in each vertex of the total dominating set, and you will see that this is k-rainbow total dominating function, so this inequality must hold. And the upper bound is tight. What about the lower bound? Well, the lower bound is tight in the case when k is equal to 2. And in fact, all such graphs were characterized by Liu and Hu. But for k equal to 3 or greater, this bound actually does not appear to be tight. We couldn't find any examples to explain what is going on this side, yeah? So we posed a question of finding a function k so that this inequality would be tight. From examples we only know that this function should be bounded by 1 and 1.5. Yeah, that's all we know. You will see that it was not so hard to obtain the bounds, but the tightness was in almost in all the cases a mystery, at least a part of tightness. Yeah. Another thing we wanted to do was to compare our invariant with ordinary rainbow domination, and again, the lower bound is tight for every k, the upper bound is tight for k2. But if k is at least 3, then we do not have a tight bound. So what is it? What is the tight bound? Is still open. And again, we know that this function of k is bounded. This is what we could find out from our examples we found. Yeah. The most interesting comparison is probably with ordinary domination, and this is something which is really easy to see. We just before we explained this bound, and because every k-rainbow total dominating set is of course dominating, this inequality certainly holds. But motivated by a question from this paper of Azaria and others, Goddard and Hennig were exploring this a little bit further, and they discovered that actual bound, so this gamma cannot be attained because actual bound is 4/3 of gamma. Yeah, and you can see one example of graphs for which this bound is tight. Well, we then managed to generalize this result to general K, to any K. You can see if you insert K into this fraction, you get exactly the bound of Goddard and Henning. And now again, what about the tightness? Yeah. We managed to construct, I won't go into details, it is too complicated to explain it right now. I would need some more time, but we managed to find graphs for which we have tight inequality. But now it gets really interesting for K greater than 4 or equal to 4. We have a conjecture that the tight bound should be 2 times gamma. And you can observe that this conjecture is certainly true for bipartite graphs because of this sequence of inequalities we saw before, and because we know that this equality holds, yeah? And we know that if we take a look at the ratio of K rainbow total domination number of this graph, which you can see in this figure, yeah? And the domination number of this graph, the ratio is 2, but we couldn't find any examples to get below 2. But from our theorem, we know that this number or function of K, which should stand here, if we are talking about the tight bound, then it should be between this and this, yeah? This is what we know so far. Okay, I would like to get your attention back to this result we saw before. As I said, it was originally proved by Azaria, Henning, and Klaujar in 2017. And their proof is, it involves hypergraphs, and it has 2 pages. I don't really exactly remember the details, but a year later, Goddard and Henning found a shorter and more elegant proof. And now that we have this concept, our proof is even shorter. It can be squeezed into this empty space here, yeah? So let's take a look. If we have a bipartite graph with bipartition L and R as left and right, and if we think of S as an optimal two rainbow total dominating function on this graph, yeah, I tried to sketch this situation. So this 1, 2 means that all vertices which are in this part are colored with both colors. This one is, those are just colored with one color, and so on. And now we define A, the set A, to be the set, to be the union of these green parts. And now I claim this A is a dominating set. This can be easily seen because we only have to check these vertices in these white spaces, yeah, in these white parts. And if I take such a vertex here, I know, because F is a 2 rainbow total dominating function, this vertex has to have neighbor 1, and it has it across here, yeah? And this is in green part, so this vertex here is certainly dominated, yeah, by A, by the set A, yeah? And also, if I check this vertex, I know that it has to see 1 and 2, either it has a neighbor here or it has 2 neighbors, 1 here and 1 here. But you saw that I made connections to green parts, so A really is dominating for these parts, but also you can easily check that these vertices here are dominated as well, yeah? And now if you switch the roles of L and R, you will in a similar way obtain a set B, which will contain this part, and this part, and this part, yeah? And this will be dominating set as well, yeah? So now we get this sequence of inequalities. Actually, there are equalities from here. this is obvious because A and B are dominating. And if we sum up their cardinalities, we get exactly the weight of our function f. So this inequality holds, and vice versa. It's just obvious. So that's it. Yeah, this is the proof, short proof of this equality. Okay, you can see the Ising's conjecture here once more. And I'm also sure that the most of you at least know this result of Clark and Suen. Yeah, we have this factor too. This was proved. And a similar result just for total domination was proved by Ho. And now using his result and our bound on total domination, we obtained that this inequality holds, but not just for our new invariant, also for ordinary rainbow domination. Yeah, we have this inequality. But we believe, we are pretty convinced that instead of this factor 2k, there should only be 2. Yeah, so we have another 2 conjectures, one for total domination version of rainbow and ordinary rainbow. And what is especially interesting here is that if we take bipartite graphs, you can see that this equality and this equality certainly hold, yeah, just by this proposition that we just proved, yeah. And if you take a look, you will see that if we restrict to the case when k is equal to 2 and to the class of bipartite graphs, then this conjecture and Ising's conjecture are equivalent. The last time I checked if Ising's conjecture is settled for bipartite graphs was maybe 2 or 3 months ago. It was still not, so this might be a new, different view on Ising's conjecture if in the case of bipartite graphs. I'm checking on time a little bit. Okay, so we are already by the third paper, in which we explored rooted products, by the way, as I mentioned. And just to recall, what is a rooted product? Well, the name comes from having a vertex H in which we choose a specific vertex, which we call a root. And then we make copies of this graph H, as many as there are vertices in G. And then in each copy, we identify this root with a vertex in G. Yeah, we can see here 2 examples. But now that we are familiar with Cartesian products, we can also say that this rooted product is actually a subgraph of the Cartesian product, right? You have these H layers, and the edges appear only in one layer, isomorphic to G, the one which corresponds to the root, yeah, in H. So you can look at it also in this way, yeah, this rooted product. And for the rooted products, with Todea, we obtained the bounds, yeah. Of course, we considered only the cases when k is less than the cardinality of the rooted product, because in this case, by observation we made previously, we obtained nothing interesting. That's why we have this assumption. And if we take a look at the upper bound for this product, you can imagine that we take one copy of H, or original graph H, we label it, and then we keep this labeling through all the copies. And with this, we will certainly get a labeling, which will be fine also in the whole product. So this bound really is, let's say, trivial. but it was not so for the lower bound. Here you see we had to distinguish some cases which surprised us a little bit at the time. Well, what I would like to mention here also is that in the case when A has a special structure, we were able to improve this bound, yeah? In this case, when K is less than the cardinality of H, yeah? What do I mean by specific structure? If I have H, and if I attach a pendant vertex to this graph, I will denote this with H plus. Yeah, and if I now take this vertex as a root, this is V, and if I take a look at this rooted product, then you can see that where we have K before, now we have gamma KRT of H. So this is better. And we also know that this bound is tight. A little bit more on this later in conclusion. Okay, so now let's move on to the next result. We were also able to easily derive the formula for the corona product in the case when NH is at least K. Why? Because we can see corona product as a special case of rooted product. Yeah, this is our corona product. Recall that corona product is, what do? We take copies of H, and then we connect each vertex in each H layer, let's say, with a vertex, with a corresponding vertex in G. Yeah, and this pink balloon with these blue edges, this graph can be considered as the join of graphs of this pink part and this vertex V. What is the join? We just take disjoint copies, disjoint graphs, and we put between every possible edge. Yeah, so this graph can be seen as the join of H and this singleton graph. So, and if we take this singleton as this as was singleton before, this vertex V, if we take it as a root, then we see that these two things coincide. So by the previous theorem, this inequality is obtained, and the opposite inequality is obvious because we can construct a K-rainbow total dominating function in such a way that we just put all the colors in these vertices of G, and that's it. Yeah? So we have closed formulas for corona products in this case. Now, the last thing about the complexity, well, recall that the dominating set problem asks whether for a given graph and a positive integer k, the graph contains a dominating set of cardinality at most k. And we ask if G has a two-rainbow total dominating function of weight at most k. Yeah. And to prove the NP completeness, we have to do the following. We have to check that two-rainbow total dominating function, this problem is in NP, which is clear. And then we derived a polynomial time reduction from this known dominating set problem to our two-rainbow total domination problem. And how did we do this? First, we took a graph which we called T, and we proved that two-rainbow total domination number of this graph is 4. So this is optimal two-rainbow total dominating function, yeah, of this graph. Moreover, if you put 1 and 2 in this vertex, we called X, then the weight of the whole function will be at least 5. Yeah, this is something we needed later. And the next step was the construction of the new graph, which we called G prime, which is obtained as the rooted product of arbitrary graph G and this graph T plus where we pull out one vertex out of X. I mean, we attach V to X, this pendant vertex, and we take this as a root, yeah? And then we observed that if F is just any two-rainbow total dominating function of this structure, then its weight is greater than 4 times the number of vertices in G. For this contribution of these green balloons, these upper parts here, is at least 4. This is also something that we really needed in the sequel. Yeah. And the main thing which led to the final goal was the following proposition which says that G prime has a two-rainbow total dominating function of weight at most K plus 4 times Ng if and only if G has a dominating set of size at most K. Okay? One way is quick. Yeah, just take a dominating set of G and without loss of generality, assume that vertices in D are denoted from G1 to GL. Yeah, we have L vertices here, and by assumption, this is at most K. And now we define function F. I used red color to define this function. And now I claim that this function is a two-rainbow total dominating function. What do we have to check? We have to check that each tooth is 2 in the neighborhood. Just by taking a look at this picture, you will see that this is so. Also, every one sees 1 in its neighborhood, also this one, yeah? And all other vertices which are empty, they see both colors in the neighborhood. This is certainly true for these 4 vertices, and so on. And also for these vertices, because they see 1 in the dominating set, I didn't say, but every color in the dominating set is colored by 1, yeah? So we have 1 as a neighbor, and we have 2 as a neighbor above, yeah? So this really is a two-rainbow total dominating function of this graph with this cardinality, which is obvious. Now I'm checking on time and I see that I should end up soon, right? And I would like to spare some time for the conclusion.
Yeah.
So, yeah.
10 minutes you have time.
Oh, I have 10 minutes. Oh, okay.
But you know, we must have a time for a question.
Yes,
So,
yeah.
yes, okay.
Yeah, okay. That's
Thank
why I thought I will skip this explanation because it really takes some more time. You can see that even the sketch is more complicated, so I will skip this part of the proof. To be able to show you maybe things that will be more interesting, what is still open. Anyway, these results that we just saw, with this we were then able to prove that two-rainbow total dominating function is NP complete, yeah? And if you take a look at this graph, you see that it is planar, and we know that dominating set problem is NP complete for planar graphs. And as soon as G is planar, then the whole graph G prime is planar. So two-rainbow total dominating function is NP complete even when restricted to planar graphs. And this was the last result we showed in this paper, which was published in the beginning of this summer. And we thought that for general K, this will be more difficult. So we left this as an open problem, but we couldn't sleep. And we were still playing around this. And in the meantime, we were able to solve this also for K greater than 3. And it turned out that even simpler construction of G prime will be useful. Instead of this T graph, we just take these subdivided stars, and with this we were able to prove NP completeness, or also for larger K. So this is still This is not published, yeah, but we know that it is so. Okay, so what is still open? Here I made a summary of open questions that I already mentioned through this lecture, so you can get back to them later, yeah? They are just here. If one wants to take a look at them later. And what else? Well, recall this proposition from before. We obtained this improved lower bound. And we tried also to characterize graphs for which equality here is attained, because that would help us to shorten arguments in the proof of NP completeness, but we couldn't succeed, yeah? And as a corollary of this proposition and its proof, we also obtained this, this is actually a sufficient condition, yeah? If this holds, then we have equality here, but vice versa, it does not hold. As you can see from the numbers here below, from this example, if you take this as H, and this here is our rooted product of K2 and our graph H plus, where we pulled out one vertex here down below, yeah? We attached this vertex and took it as a root, but the 3 rainbow total domination number of this graph is 8, yeah, while this is 7 and 14, so this equality holds, but not this one, yeah, so the opposite does not hold. And then we really tried to find graphs for which equality is attained, but we couldn't, yeah. So these 2 questions that I just mentioned are here. And another thing is, we obtained bounds for the rooted product, and for ordinary domination and total domination, in the case of rooted products, closed formulas exist, yeah? And while I was still deep in this story, I had a strong feeling that we could obtain a formula here as well, but we didn't go so far. So yeah, this is open. Can we derive enclosed formulas for the rooted products? And also in this case that was left, yeah, for Corona products. We didn't do this, yeah. And finally, we saw this upper bound before, yeah, trivial upper bound, but when is it attained? This seems to be a natural question, but I believe it might be quite challenging. Why do I think so? Because already in the paper of Azaria, for the case when K is 2, they said that, well, they named the graphs that attain this bound as prism gamma T prism perfect graphs. And they ask what is the characterization of this graph. Certainly we know that if G is a bipartite graph, then due to this equality, we know that bipartite graphs are prism perfect. And then they said that they think that this question of characterizing this is hard, but they do believe that almost all graphs are gamma T prism perfect. They show us some numbers. Why do they think so? So out of roughly 11,000 connected graphs of order 8, precisely 297 graphs are not prism perfect. And here you can see also the number. This number is small comparing to this number for connected graphs of order 9. So they believe this should be true. But they suggest that maybe if we restrict to some special cases of non-bipartite graphs, such as triangle free or something, then we can try to characterize such graphs. So maybe, yeah, that's why I believe this should be hard, and probably this even harder. But anyway, maybe it's interesting for someone. So at this point, I would like to invite you to, if someone has some idea, would like to work on this, with Tadea we have this partial result. We are open for discussions, yeah? And at this point, I would like to thank you. And then now I will leave some time for others to prepare, or maybe for some questions. Thank you for your attention.
Okay, thank you so much, Alexandra. Very nice presentation. Thank you so much.
Thank you.